this notation, d and round of d equal to the set of all complex numbers such as z, such that absolute value of z is less than 1, and round of d equal to the set of all complex numbers such that this equal to 1. Okay, we call that on this interval, okay, b and c. The Fourier transform of this function by this definition equal to this. By this definition, okay? F hat of t equal to this. So for any f in L1 f tilde or f hat from R to C defined by this, f hat of t equal to this integral. dx, okay, dx. This integral take on x, f of x e to the power of minus 2 pi tx dx. So as an example, if we consider f equal to this characteristic function, then we see that f hat of t equal to this integral f, okay, multiplied by minus 2 pi tx dx, and it is equal to integral of b to c e minus 2 p tx dx. Okay, now this integral equal to one of this. If t equal to 0, then this is equal to 1. This is equal to minus 2 Mr. Ali Al-Shahmani, do you have any question?
Doctor, not picture display, only sound.
Okay, okay.
Only sound.
I'm sorry. I share at no. I'm sorry.
Yes. Now we have a picture and sound. Thank you, doctor.
Thank you very much. Thank you. I'm sorry. I forgot that I share my desktop. I'm very sorry. I'm very sorry. Thank you, Ali. I repeat, this object again. The title of our discussion is Fourier transform. Okay. And we read Fourier transform on L1 of R. I mentioned that if we consider Lebesgue measure on R, this Riemann integral equal to this Lebesgue integral, and we can define LP of R, the set of all f from R to C such that this integral be finite. Okay, we know this definition, but we have this definition for this session. Fourier transform for any f in L1 of R, the Fourier transform of f is the function f hat from R to C defined by this equality. F hat of t equal to this integral of f of x multiplied by this exponential function dx, so that for any f in L1 of R, f hat is this function. Okay, now we take an example. Okay, if we consider this characteristic function phi of b and c, we want compute Fourier transform of this function. Okay, dear students, do you have my voice and do you see image? I'm very sorry for this problem. Okay, for this Fourier transform, by our definition, f hat of t equal to this integral. This must be put instead of f. Okay, and this is equal to this function, this integral, and this equal to this. Minus 2 ptx b and c, because the derivation of this equal to this, okay? And so is equal to minus 2 pt e minus 2 p tc minus 2 ptb, okay? I write this is equal to this. Sorry. Okay. And so I omitted I to P because we have this I to P I T X, okay? And this is I and this is I. Okay? And if we multiply I to these two, we can write this I2 equal to minus 1, okay? So that we can write I and then omitted this I. So this equal to this fraction. And as another example, if we consider this function f of x equal to e by this power, then the Fourier transform of f equal to this, f hat of t equal to this integral. This is our f, this is our function that must be multiplied by this, okay? And this integral equal to these two if x be negative or be positive. If x be negative, the absolute value of x is minus x, so that this is equal to e to the power of 2px, that must be multiplied by this. And if x be positive, this equal to x. This integral equal to this integral equal to this. These two are simple because, for example, if we consider this integral e to px, Okay. This integral e to px e minus 2 pi tx dx. Okay, minus 2 pi tx dx is equal to limit of, for example, a to 0 e by this power 2p or 2px 1 minus it, okay, dx whenever a tend to minus infinity, okay, minus infinity, and this is equal to this limit two p 1 minus it multiplied by e2px 1 minus it zero and a. And this is equal to if we put 0 is equal to 1, so that this is this fraction, and if we put a is equal to 2p by this 2pa. Okay, now we must take limit whenever a tend to infinity or minus infinity, okay, minus infinity, and if a tend to minus infinity, this tend to 0, okay, so that all of this equal to this real number or complex number, okay. And similarly the second integral equal to this, and so we can write this summation equal to this fraction. This is very trivial because is equal to two p one minus it, one plus it, and 2p 1 plus it plus 2p 1 minus it, okay, and we can delete this 2p and this equal to t2 plus 1. Okay, so that we have this example. If we consider this function, its Fourier transform equal to this. Or we can write for example, we have this conclusion. This equal to this, okay, t2 plus 1. The Fourier transform of this function and we must write the same variable so that we can write this. Okay. Okay. For this function, its Fourier transform equal to. Now we have Riemann-Lebesgue lemma. Suppose f belongs to L1 of R, then f hat is uniformly continuous on R. Furthermore, we have this relation and the limit of the Fourier transform at infinity equal to 0. Equal to 0. The proof is easy. We know that this equal to 1. You know that for any alpha, for example, for any alpha, in R, we know that E by this power equal to this. Okay. So that the absolute value of this equal to 1. For any alpha, we have this. And this is an alpha. And by the definition of Fourier, f of x, E by this power dx. And we know that this is less than or equal the integral of this absolute value. Okay. But this equal to 1. So that this is less than or equal, what is equal exactly? This integral. and this is equal to norm 1. We know that this is norm 1 of f, okay? Norm 1 dx, and this is equal to norm 1 of f. So that for any t we have this is less than one norm of f, so that the infinity norm of this or the supremum norm of this f hat is less than this value. This less than for all t, so that the infinity norm of f hat is less than or equal one norm of f. This holds for any f in L1, okay? And this is very useful, so that for any f in L1 we have this relation. Now if is the characteristic function of bounded interval, then the formula in example 11.48 we see this, okay? The Fourier transform of this equal to this. This example shows that if hat is uniformly continuous on R and this limit equal to 0. This is very trivial that this function is uniformly continuous, because this function is uniformly continuous, and if in t equal to 0, the limit of this equal to c minus b, okay? The limit of this PICT minus E 2 PIBT, okay, divided by this two PT t tend to 0 is 0 divided by 0. So by the Hospital theorem it is equal to this limit by the Hospital theorem, okay? T tend to 0 let me write in this T tend to 0 Okay, minus 2 p IC by this power minus 2 p ICT and minus or plus 2 p IB E by this power BT, and the derivation of 2pt equal to 2p. Okay, now if t tend to 0, this equal to 1 and this equal to 1, so that is equal to you know that I2 equal to minus 1, so that is minus 2, sorry, plus 2p, 2p C, and this equal to minus 2pb divided by 2p, and this equal to C minus b, and this is equal to f hat of 0, so that this function is continuous at 0 and also continuous in all non-zero real numbers, so that this Fourier transform is continuous. And it is trivial that the limit of this at infinity equal to 0, so that we see that by this example, if f equal to this characteristic function, f hat is uniformly continuous and this limit equal to 0. Thus the same result holds for finite linear combination of such functions. Okay, if we consider any finite linear combination, f equal to, for example, this linear combination alpha I, bi and ci, then f tilde of this equal to linear combination of Fourier transform of these functions, this is equal to this. Okay, this is very trivial, and we know that all of these are uniform continuous, so that f tilde is uniform continuous, and also is uniformly continuous, and also this limit equal to 0. Because all of these functions have this property. Okay, so So, Walaikum Assalam, Abdul Rahman and other students, welcome. Thus, the same result holds for finite linear combination of such function. Such finite linear combination are called step function. Okay? Now consider arbitrary f in L1. There exists a sequence such as fn of a step function such that this limit equal to 0. This is the famous theorem that we read in real analysis 1, and in this book is this proposition. Thus, this must be 0. By this relation, we prove this relation for any f in L1, okay? So that f tilde minus f car f tilde or f car minus f tilde node infinity equal to or less than or equal nor one of these, and this is equal to f car hat minus f. This tend to 0, so that this must be tend to 0, okay, by this relation. In other words, the sequence fn hat converges uniformly on R to f, to this f hat, because the uniform limit of uniformly continuous functions is uniformly continuous. We can conclude that f hat is uniformly continuous. Please note that we see all of these functions are uniformly continuous, so that this must be uniformly continuous, okay? Let me write this for you. For any k in natural number, this function is uniformly continuous and this function, this sequence tend to this function uniformly these two lead to this fact that this function is uniformly continuous. Uniformly continuous. Okay. So that f hat is uniformly continuous because the uniform limit of uniformly continuous functions is uniformly continuous. We can conclude that f hat is uniformly continuous for term. The uniform limit of function on R such of which has limit 0 at plus and minus infinity also had this limit. This is very trivial that this limit equal to 0. Limit of this equal to limit of f hat is the limit of f car, okay? Plus or minus. This f hat equal to this limit. Okay? K tend to infinity. K. But this is equal to this limit by uniformly continuity, okay? We can replace these two limit, then limit f k t tend to plus or minus infinity, and this is equal to 0, so that this is equal to 0. Okay? It is not that we use sometimes this fact that if, for example, we consider two functions in L1, then f1 plus f2 hat equal to f1 hat plus f2 hat, and this is very trivial because we know that, for example, if we consider any t in real numbers, f1 plus f2 hat of t equal to this integral, okay? f1 plus f2 of x e by this power itx dx, and this is equal to these two integrals, f1 of x by this power and f2 by this coefficient, and this is equal to f1 of t and other f2 of t, okay? Let me write, this is equal to this and this, okay? And also we can consider a coefficient for f2 such as this. It is very trivial because is alpha is in this, and finally we have this property, okay? Okay, alpha and alpha. Okay, so that we have this relation. Dear students, do you have my voice? Don't have any problem? Thank you. Also, we have this proposition. Suppose f belongs to L1 of R, define g from R to C by this function rule, g of x equal to x multiplied by f of x. If g belongs to L1 of R, then f hat is a continuously differentiable function on R. This is continuously differentiable. In the previous session, we see that f hat is uniformly continuous, and in this proposition we see that f hat is uniformly differentiable. Okay, if this function belongs to L1, and also we have this equality for all t in R. For the proof of this proposition, fix t in R, then we see that this limit equal to this. This is trivial because, let me write this for you, f hat t plus s the limit of f hat t plus s minus f hat of t tend to s. Okay, oh sorry, s tend to 0 equal to this limit this multiplied by f hat of t plus s equal to this integral f of x by this power minus 2 pi t plus s x dx, okay, minus this integral f of x e minus 2 pi tx dx dx. dx, and this is equal to this limit we can write one integral this minus this by the first integral equal to this minus 2 pi tx multiplied by minus 2 pi ts or sx I sx is if we multiply these two exponential function this equal to this, okay, minus f of x e minus 2 pi tx, then d of x, and we can factor this function to see this relation, okay, this relation minus 2 pi x is in the book use s, okay, s tend to 0. We write same notation s, and this is equal to this limit we can move this to it is equal, but in the book consider s. Let me change this to s2 so that this is 1 on s, okay, and this limit equal to the limit of this integral f of x e by this power then this function e minus 2 pi sx and minus 1 s dx, okay, because this move to this integral and we can write this fraction. And now is equal to this limit. This is very important. We can move this limit to this integral. We can replace the limit and integral by the dominated convergence theorem. Okay, is equal to the integral of limit, so that we can write, okay, f of x by this power, and this limit s tend to 0 is held by DCT, dominated convergence theorem. Okay, DCT, dominated convergence theorem. So you can see that this limit equal to 0, and by Hospital theorem again, the enumeration and diminution of this fraction in 0 equal to 0, so that by the Hospital theorem this limit equal to this limit by the Hospital theorem. Okay, is equal to this integral and this limit minus 2p ix and 1 s tend to 0 dx. It is not that we write instead of this limit, okay, by the Hospital theorem. Derivation of this equal to this. Sorry, I omitted one. The derivation of this equal to this minus 2 pix e by this power. Okay, 2 pi sx. Derivation take on s, so that we have this coefficient. And this limit equal to this coefficient, so that this equal to minus 2 pi minus 2 pi Then this integral x f of x e minus 2 pi t x dx, and this is exactly the Fourier transform of x f of x, and this is g. We know that this our function g. Okay, this is our function g of x. So that this is Fourier transform of g. This our function g. Okay, g of x. If we consider this function x f of x, so that we see that this limit equal to this, so that the derivation of f hat equal to this function. Okay, the derivation of, because this equal to derivation of f hat on t, f hat on t. As a conclusion, f hat prime let me write f hat prime of t equal to minus 2 pi g hat of t. Okay, g hat of t. And we prove this equality. But it is very important that we use dct for replacing limit and integral, because we assume that this function is an integrable function. Okay, this function is integrable. Because this is less than this function, and this function is integrable. Please read the dominated convergence theorem. We express this theorem in real analysis 1. Okay, all of this is less than this, and this is integrable function, so that we can replace limit and integral. Okay, I think it is enough to this session. We will continue in the next session. Dear students, do you have any questions? Do you have any questions? Next week, inshallah.